Okay, so let's talk about Hess's law of additivity of reaction enthalpies. What a great word. You'd think I made up that word, but chemists actually use it. Additivity. What a great thing. It simply means that we can take a group of chemical reactions that are linked in some way. It's not like we just randomly take chemical reactions, but we can take a series of chemical reactions that add up to a final chemical reaction. And if we want to know the enthalpy of that final chemical reaction, we simply have to add up all of the individual enthalpies. Now that's essentially Hess's law right there. You didn't write anything down. All these words blew right past you, and it doesn't make a whole lot of sense at this point. But it really is a simple thing. It's a very straightforward addition of chemical reactions. Let's talk about why we can do such a thing. Now, some rationale first. Let's say that we wanted to study the heat given off when magnesium burns. You've all seen the combustion of magnesium in probably grade 9, 10. Some teacher sticks a piece of magnesium ribbon in the flame and glows bright and all that type of stuff. Super, super hot, right? That flame is one of the hottest flames that we actually encounter in a high school lab. It's got to be about 1,200, 1,500 degrees, right? The only thing that I've seen mark our lab benches is burning magnesium falling on the lab bench. I did it once, anyway. So that's the only thing. It's super hot. And if we wanted to calculate the heat given off in a combustion reaction like that, and we don't have a big bomb calorimeter that can take something like that heat, and we only have styrofoam cups, we need to do something a little different. Because if you were to take burning magnesium and drop it into some water, that's a super dangerous situation. That actually becomes explosive, all right? You can't put burning magnesium out with water because the superheat of the burning magnesium actually causes the water to decompose into hydrogen and oxygen, and then it quickly recombines and gives its energy back out in an explosive manner, and it literally causes an explosion. So, number one, it's explosively dangerous. Number two, you drop some magnesium in a coffee cup styrofoam calorimeter, and it hits the side, and you melt right through the calorimeter, and it's really a mess. You really just can't do it. So if we wanted to study such a thing, how can we do this? Well, there are many other chemical reactions that we know that magnesium can undergo that are not dangerous. We could take magnesium metal, and we could put it in an acid, and we could have it react with the acid and bubble in a single displacement reaction, make some hydrogen gas, make some magnesium chloride, and that is still a reaction that contains magnesium and starts the process of breaking that magnesium down. If we could come up with other magnesium reactions that we can add together, literally add them up, like we're adding algebraic equations, and those series of equations then can be added to our combustion of magnesium equation, then we can get what that reaction is by adding up the easier equations. There are many chemical reactions that don't occur in aqueous solutions or release too much energy that we cannot do in a coffee cup calorimeter. Usually these reactions can be broken down into a series of simpler reactions or steps that when combined, so when we add them together, have the same initial reactants and final products as the original reaction we want to do. The delta H's for such a reaction can be determined using Hess's law, and now you can write down Hess's law. You don't need to put the heading, I guess, but this is the statement of Hess's law. The delta H for any reaction that can be written in steps equals the sum of the values of the delta H for the individual steps. So it's all about adding them up. As an equation, it looks like this, but this is one of these equations that I never have you actually directly use. When I show you how to solve a Hess's law problem, we never actually write that equation down. This equation is simply a mathematical representation of Hess's law. When we do a problem, we we solve it using a handful of steps that never actually involves writing that equation down. So if you're someone who likes to put a star beside equations that are important, that we use over and over again, like our molar enthalpy and our calorimetry, don't put a star by this one. We don't actually have to memorize that equation. We don't ever use it in that form because there's an easier way to write down the problem when we get to this. Now the next slide involves a little potential energy diagram. We've seen the potential energy diagrams before. You saw them when you did the lesson on thermal chemical equations, how we can represent a chemical reaction in terms of its potential energy and its reaction progress, and how we can have reactants and products, and whether it's exothermic or endothermic. You know, we can then see whether that energy is being given off or energy being added. This next slide talks about how we can then think about Hess's law in terms of a potential energy diagram. And I don't know if I'd write this down, but it's just a way of thinking about why we can do such a thing. And I'll give you another example in a moment. But let's say that we took some methane gas, CH4, and we burnt it, and we ultimately wanted to get the products, which is carbon dioxide gas, and after it cools down, the water would liquefy, and you get some condensed liquid, say on the outside of a test tube. Think back to our good old Bunsen burner experiment. Actually, I got piles of labs. I'm marking the grade 11 Bunsen burner experiment. And think about when you first put that cool test tube into the flame, you see a little bit of condensation on the test tube. If you've ever cooked with natural gas, like if you at home have natural gas or propane that you use on your stove, when you first put that pot on there, if it's cool, like if you got frozen veggies in the pot, you know what I'm talking about? You get condensation on the outside, right? You've seen that before? All right. So for that reaction, what you have is methane gas burning with oxygen to produce carbon dioxide and liquid water. And that's exothermic to the point where 890 kilojoules per mole of methane is given off. But in actual fact, that reaction takes place in two steps. Because right after the combustion takes place, the water is actually in the vapor state. It's actually in a gaseous state. And then once the water vapor touches the cold pot, it condenses and becomes a liquid. The delta H for combustion that results in gaseous water is only negative 802 kilojoules. But then the delta H for the change of state from a gas to a liquid, which is also endothermic, is another 88 kilojoules. Whether you think of the reaction as being one step all the way to liquid, or two steps, combustion to the gas and then condensation to the liquid, it doesn't matter. It still results in the same amount of energy. So you can take a chemical reaction, and if you can express it in a series of simpler chemical reactions, the entire delta H for that reaction can be determined by adding up the delta H's for the simpler reactions. That's what Hess's law is. You can actually take a chemical reaction that's complex and hard to study, break it into simpler chemical reactions, add the delta H's up, and get the total delta H. So we're simply adding chemical reactions like they're algebraic expressions to get the overall delta H. Let me give you another example of why we can do this. All right. This is essentially a version of the law of conservation of energy. Let's say that you were stuck on a cliff here. All right. So you're stuck on the cliff, and you ultimately want to get down to the lower level, right here, and it's going to take so much energy for you to get down there. And in this case, it's actually gravitational potential energy, EG. I'm going to turn this into a little physics problem, right? And if you wanted to get down there, then there's many different ways you could get down to that lower level. If there were some steps built in, you could then take a whole bunch of little steps So if you had a whole bunch of steps here, you could take the steps and you could get down there very safely. And you could add up each of the little gravitational potential energies for each of the steps, and that would get you down to the lower level. Or if you were, a daredevil, you could like just jump right off. Probably break your legs, who knows. Wouldn't be very, very wise. But again, the energy that you would transfer to your body would still be the same as all of those little steps. You could even, we could make this silly, which I tend to do things like that. You could imagine that there's also an option to take a roller coaster, right? It doesn't really make any difference. You could get on a roller coaster. You want me to put the car on the roller coaster too? Man, Lauren's looking at me like she can't, she's having difficulty visualizing the roller coaster. Anyway. And again, your speed would increase and decrease, and you'd have all these changes in energy, but in the end, if it was perfectly frictionless in this case, you would still end up with that same amount of gravitational potential energy. And that's because we have what is called the conservation of energy. And so it doesn't matter how you get to that final location, it's the final location that determines the overall energy. When you continue on in science, they'll call something that is only dependent on your beginning and end position. Has nothing to do with how you get there, right? They call that type of a thing a state function. And I always was confused by that. It really caused me a lot of pain, even after university. Why was that called a state function? And I was always thinking of changes of state and things like that. But they mean it's only dependent on its initial state, in this case, height 1 versus height 2. And the final state. It's only dependent on that. And it's not dependent on the path you take to get to the final state. All right? So something like gravitational potential energy is a state function. It just determines on how you, from A to B, doesn't matter what path you take. Now, if we were to add friction into that, let's say you added friction, like air resistance and the roller coaster's wheels friction, then friction takes some of that energy away. It sucks it away. The longer the roller coaster you have, the more energy would be sucked away. As soon as you put friction into it, it's not a state function anymore, because it depends on the path you took to get there, all right? So if we had an ideal situation here, it's a state function. Chemical reactions, because heat at a microscopic level doesn't just disappear, right? You've got to have a conservation of energy. It's a state function. So if you're starting with reactants and you're ending up at products, it doesn't matter whether you do it in one shot, one chemical reaction, or you do it in 1, 2, 3, 4 different simpler chemical reactions. As long as it ends up in the same products, it's going to be the same amount of energy. You just add up the steps. And that's because energy is a state function. It has to do with that. Okay. So when we start manipulating our questions in order to solve the problem, sometimes we need to flip a chemical equation around. Sometimes we need to make the reactants products and the products reactants. In other words, just a little left-right flip. When you reverse an equation, you're essentially making reactants products, products reactants, which essentially turns an endothermic into an exothermic, or an exothermic into an endothermic. You flip what the reaction becomes. And therefore, when you flip the reaction, you also change the sign of the delta H. And I do that step very algebraically, all right? I simply say if I want to flip it, I'm going to multiply the entire reaction by -1. A flip and change the sign on the delta H. Very simple. Sometimes I need to multiply a reaction by a factor. Sometimes I need to double it. I could multiply it by a half, but that gets into, fractional coefficients. If we can avoid fractional coefficients, it makes life a little easier. But if you change the reaction, if you double the reaction, you've got to double your delta H as well, because you've made it twice as big, right? You've multiplied everything by 2. All right, those are the rules. Then when you're done and you get what you want, you add it all up and you've got it. You've got the answer. So in our first reaction, we have to determine the enthalpy change for the conversion of an ethane molecule, C2H6, to an ethene molecule, C2H4. Here's the reaction that represents the overall reaction that we want to study. You'll notice that our ethane molecule has 2 extra hydrogens than the ethene, and so essentially we want to remove a hydrogen molecule from our original molecule. Now we want to determine the energy needed to remove this hydrogen molecule. Now this reaction is difficult to do in the laboratory and even more difficult to measure the heat involved in such a chemical reaction. We do, however, have the energy involved in combusting these 2 molecules. And these 2 reactions can be easily done in a bomb calorimeter, and using calorimetry that we already know how to calculate, we can easily calculate the enthalpies of reaction. We can also determine how much energy is needed to combust hydrogen and oxygen to produce water molecules. And if we use Hess's law correctly, we should be able to manipulate and add these equations together so that we can get the overall equation that we desire. So this next slide, I've just taken those reactions and I've moved them up so I've got some room to do some calculations. And now we want to manipulate each of our reactions so that we can get the C2H6 as a reactant and the C2H4 and H2O as products. So if we take a closer look at the first reaction, you'll notice that C2H6 is already existing as a reactant in our combustion reaction. And therefore, when we add this reaction to the rest of them, we will result in a C2H6 as a reactant, which it is. And so for reaction 1, I do not have to manipulate it in any way. I don't have to change it in any way. So this reaction is good to go. If we look at the second reaction, you'll notice that the C2H4 is also a reactant. But in the reaction that we want to obtain in the end, our C2H4 is a product, which means at some point in time, I'm going to have to flip this reaction around, changing the reactants to products so that this reactant ends up as a product so that when we add at the end, it is also a product. So if I want to turn this into a product, I need to flip the reaction, and mathematically, that is the same as multiplying the reaction by -1. So that's the multiplier for reaction 2 that will result in the reactant C2H4 becoming a product C2H4. All right? I guess if I go back to reaction number 1, because I'm not changing that in any way, I'm essentially going to multiply it by 1. That's going to be no change, but I can assign a multiplier to it. If we now take a look at the final reaction, we will notice that hydrogen is a product with a coefficient of 1. In my third reaction, I have hydrogen as a reactant, but with a coefficient of 2. That means I need to flip this reaction, multiplied by -1, and I also need to divide this reaction by 2 so that my 2H2 becomes 1. So I need to flip and divide by 2, or flip, which is negative, and multiply by 0.5. And so there's my multiplier for the third reaction. Okay, now let's do that particular situation. So number 1 times 1, no change, so I'm going to rewrite C2H6 3.502 to CO2 and 3H2O liquid. And my delta H is -1559 kilojoules, and we're going to multiply it by 1 because that's what I did to the reaction. So essentially it's no change. Let's continue with the second reaction. Now the second reaction I'm going to multiply by -1, which means I'm going to flip it. I'm going to first draw the arrow because I want all my arrows to be in a row so that when I add up my reactions, I don't make any mistakes. So now let's start with the products and put them on the reactant side. 2CO2 gas, 2H2O liquid, And now my reactants are on the product side. C2H4 gas plus 3 O2 gas. And the delta H. Even though I flipped it, I like to rewrite the delta H for the original reaction and then add the multiplier. In this case, multiply by -1. So that -1 will change this to a positive, which essentially turns it into an endothermic reaction as opposed to the original exothermic reaction. Now let's deal with reaction number 3. Flip and divide by 2. Again, I want my arrows to be above and below each other. Looking at the H2O, taking that 2 and dividing by 2, that leaves me with 1 H2O liquid. Flipping, now looking at the 2H2, that's going to leave me with a single H2 gas molecule. And taking that O2 and dividing it by 2, we're going to be left with 0.5 O2 gas molecules. And again, the delta H. I rewrite the original 572, and I multiplied by -0.5, so I'm going to put the multiplier -0.5. All right. So now the first thing we do is we check to see if our reactions add up to the desired reaction. And we do this simply by canceling out things that appear as reactants and products, and anything that doesn't cancel out, we leave. So CH6, there is no C2H6 on this side, no cancellation. 3.5O2. Well, there's 3O2, and there's 0.5O2. So that means all of the O2s, 3.5, cancel out 3.5. And that's good, because there is no O2 in my final reaction, and we expect it to cancel out. Let's take a look at the CO2s. 2 CO2 on the left, and 2 CO2 on the right, and those cancel out. All right, looking good. And now H2O. 2 H2O and another H2O on the left makes 3 H2O, and that makes 3 H2O on the right. And we cancel out those H2Os. And you'll notice we are left with what we needed in the end. And that's because we picked our multipliers correctly. So I'll rewrite now everything that's left. C2H6 gas, no other reactants, everything else is canceled out. Arrow, C2H4 gas, and notice we also have the H2 gas. And that is the reaction that we wanted, and therefore our multipliers are correct. And therefore, if we total up our enthalpies, we will have the enthalpy for this reaction. So as I put it through my calculator, I'm going to have -1559, and I'm going to add, right, 1411, and here I'm also going to add, and then I've got to take 572 and divide it by 2. And when you run that through your calculator, you will get positive 138 kilojoules. All right? And that means for this reaction that is difficult to do in the lab and difficult to measure, we have determined the enthalpy for that reaction. All right? Now that's not a molar enthalpy, that's just a total enthalpy for this particular reaction. But we could turn it into a molar enthalpy because there is only 1 mole of each of these reactants. We could say that the delta H for this particular reaction is equal to 138 kilojoules per mole of C2H6. And again, remember, when we're talking about molar enthalpies, it's always with respect to something. So for each C2H6 that reacts, we will need, it's endothermic, 138 kilojoules. Okay, let's do one more example here. So determine the enthalpy change if 10 kilograms of HCl was reacted with an excess of O2 according to the following reaction. Now this time we're dealing with a number like 10 kilograms, and we will deal with that at the end. And ultimately though, we need to get how many kilojoules, right? What's the delta H for this reaction? That's going to be Hess's law. And then we have to do a little add-on calculation at the end to figure out how much 10 kilograms is going to produce. So just like the last reaction, we're going to manipulate these reactions here to determine the multipliers so that we can get this final reaction. Okay. Again, I'm going to use the same process. I'm looking at the reactants and products in my final reaction, and I'm going to manipulate these equations to get that desired situation. I have 4 HCl's as reactants, and so now I want to locate HCl in my 3 reactions, and I want to put it as a reactant with the coefficient of 4. So you can see it's located in reaction 1, but it's a product with a coefficient of 2. So I'm going to multiply this thing by -2 because that's going to flip it, and it's going to turn the 2 to the 4. Now let's take a look at the second reaction. I see oxygen gas in here, and I see an oxygen gas here. I have a half. I need 1. No need to flip. I'm just going to multiply that guy by 2. And now you'll notice in the third reaction, I have water vapor versus water liquid, and I need 2 water vapor as products, which means I need to flip and multiply by 2. Again, let's rewrite and see what we get. So -2 that's aqueous. Again, I want all my arrows to line up. 2H2 gas, 2Cl2 gas. And delta H is equal to -185. And what did we do? We did -2. Reaction 2, we've predicted we're just going to double it. 2H2 gas. Oh, and I didn't line up my arrows very well. I hope I can fit it in. 1O2 gas. We're squeezing it in. And then with the flip, oh no, we're not flipping. We're just doubling. 2H2O liquid. And that is -285.8. And we are multiplying it straight up by 2. No negative on that one. Last one, flipping and doubling. So again, let's get my arrow down so I don't screw that up again. H2O liquid, because it's a flip, and I'm doubling it. And H2O gas on the other side. Delta H, because I've doubled that reaction, I need to double it, -40.7. And I flipped it, so it's a -2. Again, just like in the last situation, we're going to cancel. And I want to get rid of anything that's not in this reaction. So I want to get rid of H2s. 2H2, 2H2. And I've got lots of H2Os, but notice I've got the liquid on the right here and the liquid on the left here. So those liquids are gone, and now I'm left with the gas. And I think that's all. I think I can now rewrite. So all the reactants for HCl aqueous. And what else have we got? We've got an O2, and it's a gas. And on this side, we've got 2Cl2, and it's a gas. And we've got 2H2O, and it's a gas. And you'll notice we have achieved the desired reaction, and therefore we can total this guy up. And again, if we total this guy up by multiplying our factors in and then adding, you should get out of your calculator -120.2 kilojoules. Okay, now this reaction is how many kilojoules we get for 4 moles of HCl. We want to figure out how much energy will be produced if we start with 10 kilograms of HCl. 10 kilograms HCl. In the end, I need to find out joules, And we know that we've got negative 120.2 kilojoules being produced for 4 moles of HCl. So in the end, I'm going to need to convert this mass into moles. So mass into moles, I need a molar mass of HCl, 35.5, 1, 36.5. So let's start with 10 times 10 to the 3 grams HCl times 1 mole over 36.5 grams, just like we used to do. And now we need a conversion factor that will turn these moles into energy. And we can take that conversion factor right out of the balanced chemical equation. We can say that for 4 moles of HCl, negative 120.2 kilojoules of energy will be produced. All right? It's exothermic. It will be given off. So notice, our grams of HCl turned into moles of HCl, and our moles of HCl turned into kilojoules of HCl. And now I'm going to calculate. And that gets me 8,233 kilojoules. And it looks like we're dealing with 3 significant digits. So 8.23 times 10 to the 3 kilojoules of energy would be released. So in this case, our problem consisted of 2 parts. Number 1, it consisted of using Hess's law to figure out how much energy would be produced. And number 2, we used some good old-fashioned conversion factors so that we could figure out how much energy overall would be produced in that reaction. Oh, by the way, negative. Negative. It is exothermic. It is giving off energy. So there is some homework that you can complete out of the textbook. If you were to cut and paste this link into a web browser, it would bring you to a site where you could generate your own Hess law questions, and you could then work on some extra problems that way as well. This is a good site that contains all kinds of different chemistry questions that you could generate and generate your own practice problems.